Hey everyone. All right, this is a quick review lesson on implicit differentiation, but then I'm also going to introduce something new called logarithmic differentiation, which logarithmic differentiation rarely comes up in this course, but it's a pretty useful tool down the road for those of you that take other calculus classes. But implicit differentiation definitely pops up. So what is implicit differentiation? I have another video from last year that goes way more into detail, but we did a lot of implicit differentiation last year. So for example, problems will look like this: x squared y plus y cubed equals 4x. And you have to find dy dx. Find the derivative of y with respect to x. Now, the thing that's different here is that all of the y's and x's are mixed together. This is given implicitly, or this is a function given, well, it's not a function, it's a relation, because if you were to graph this, I'm pretty sure it would overlap itself. There'd be multiple outputs for one input. So this is a relation, but we can still find the rate of change of y with respect to x using this process called implicit differentiation. The way it works is, and we're going to be doing this a lot for the next few days because we're going to start something called related rates pretty soon. You just take the derivative of everything like normal, except when you take the derivative of any variable, you have to include the rate of change of that variable with respect to x because we're taking the derivative of the entire relation with respect to x. So in other words, watch. I think you'll remember how this works. So this first piece, I'm going to take the derivative of this. It's a product rule. So we take the derivative of the first term, which is 2x. And now I mentioned this last year, but we never really did it because I didn't want to confuse you. But we took the derivative of x with respect to x. And that rate of change, how x changes as x changes, is just a constant ratio of 1, which is why we never really include it. But it is there. And then we multiply it by the original second. Plus, now we do the derivative of the second term, which is 1. The derivative of y is 1. But I took the derivative of y with respect to x. So I need to include a dy dx times the original first. Okay, so anytime you take the derivative of a variable when you are doing implicit differentiation, you always have to include the derivative of that variable with respect to the derivative of the variable you're taking the derivative of, which is a little confusing. But in other words, if you see y's, you need to include dy dx. If you see x's, you don't technically need to include this because it's just 1. So plus, then we will take the derivative of y cubed, which is 3y squared. And again, we took the derivative of a y term, so we need to include dy dx. Equals, and then the derivative of 4x, which is just 4. We could put dx dx, but we don't need to do that because dx dx is just 1. So in other words, when you simplify, you have 2xy plus dy over dx times x squared plus 3y squared dy over dx equals 4. All right, so now we need to get all of the dy dx terms on the left, typically is easier, and all the non-dy dx terms on the other side, and then factor out a dy dx on the left. So I'm doing 2 steps at once here. If that's just confusing, go back and watch the other video. But in this term and this term, I'm going to factor out the dy dx, and I'm going to keep an x squared plus 3y squared equals, and I'm going to do 4 divided by 2xy. Nope, you messed me up. Minus it. Minus the 2xy over. Okay, so you always subtract over the other terms first. And then we divide. So you subtract over the terms you don't want, and then you factor out the dy dx, and then you divide. 4 minus 2xy all over x squared plus 3y squared. Done. And that's the derivative. Oops. Whatever. I don't know how to go back. Notice that the, maybe this one, no, it's probably gonna mess it up. Notice that the x and y is both present in your solution. Now, a couple other things that we'll talk about in class during the performance task. If I want you to make a tangent line, you plug both x and y in. So, for example, in a problem like this, if I give you the x coordinate, you have to plug y into the or x into the original to get y, and then once you have both, you plug it into the derivative to get the slope, and then you can make your tangent line. And last year I showed you a really neat way in Desmos to check your answer by making a movable tangent line. So if you remember that, you can go watch the video to refresh yourself on how you can check your answers. But these do pop up on the AP test quite a bit. They want to make sure you are able to take the derivative with respect to x in this case, and with y's mixed around to still find dy dx. All right, so if you need more examples, there are more in the other video. I'm not going to do more examples here. I'm going to show you something called logarithmic differentiation. Okay, so what on earth is logarithmic differentiation? We did not do this last year. We don't do a lot of it this year, but it's a very neat strategy for when you have something like this. Let's say you have something like x to the x power. That's not an exponential or polynomial, because look, x is the term being raised to a power, and x is also the exponent. So this is x to the x. This is actually one of our fastest growing function. If you tried to graph this in Desmos, it would shoot up very quickly. So how do you find the derivative of something like this? We don't have any derivative rules for this. So I'm going to tell you right now, anytime you see x in the exponent and x in the bottom term here. So when you have x as an exponent and x as I'm going to call that the base, I guess. There could be other things here too. You could have x squared up here. You could have 3x in the base. Doesn't matter. But if you see x in the exponent and x in the base, you're going to use this one little trick called logarithmic differentiation. And here's how it works. When you see this, immediately you're going to take the natural log of both sides. We are allowed to do one side, whatever we do to one side of an equation, we can do to the other side of the equation. So taking the natural log of both sides doesn't change anything. It's still equal. Why did we want to do that? Well, there's a very nice log property that says if you have a log of something to a power inside like this, I can swing the power in front. So natural log of y equals, and I can swing the power in front. We got rid of the x in the exponent, which was a key goal, because now all we have to do is use implicit differentiation. And we can find the derivative. So let's do implicit differentiation. The derivative of natural log y is 1 over y times, we took the derivative of a y term, so dy dx, equals, take the derivative of this side, this is a product rule on the right, so x, derivative of x is 1 times original second, plus derivative of natural log x, which is 1 over x, times original first. So we get 1 over y, dy over dx, equals natural log of x plus 1. Oops, I did not want to do that. Does this undo? Nope. Whatever. Get out of here. We're not done. So the thing about this is once you get dy dx by itself, you multiply over the y, and you'd have natural log x plus 1 times y. And this answer is not great for one reason. The original problem started as an actual function. Look, y was isolated. We had this defined explicitly, where x's were all on one side and y was isolated on the other. So I would like to get this without y in your answer at all. So how do we get rid of y? Well, y equals x to the x. So dy over dx equals, and in place of y, we put x to the x, because that's what y equaled in the original setup. And I cannot draw boxes today. That's your answer. And we could check it. We could, actually, I'm going to do that just to make sure everything worked the way it was supposed to. So in Desmos, bam. Remember, I want you doing this while you are testing derivatives. Derivatives should be a basic part of this course at this point. So x equals x to the x, like I said, super fast growing function. Interesting, it actually decreases for a little bit and then increases very, very, very quickly, super fast growing. So I can find f prime of x. There's its derivative in blue. I can graph this other component, which was ln x plus 1 times x to the x. and just like it's supposed to, they overlap each other, which means the derivative is correct. So this is called logarithmic differentiation. You essentially have the problem of x in the exponent and in the base. So in order to get rid of this, you can simply swing the x in front after you take the log and then go from there. One more side note, which I might as well mention. So for some of you, you're like, I'm never going to be able to remember the derivative of 2 to the x, let's say, or a to the x. Well, I guess in this case then, if you really don't want to memorize the derivative, you can use logarithmic differentiation here and find the derivative without having to memorize it. Log both sides, swing the x, and now take the derivative. 1 over y equals the derivative of natural log 2 times x. Just think of natural log 2 as a number. So the derivative of a number times x is just the number. And then swing the, dy dx. And then swing the y over to the other side. So you have dy dx equals y ln 2. And then put y back. Y back. Dy dx equals 2 to the x ln 2. See? So you don't even have to memorize 2 to the x if you really don't want to, even though it's worth memorizing. You can derive it yourself using logarithmic differentiation. All right, that's it. My dog's getting mad, but we'll practice more logarithmic differentiation and implicit differentiation in class next week. Cool. Goodbye.